Section 6.5 is about special systems. So these would be systems where you end up with no solution or infinite solutions when you solve them. The best way to go about this is just to look at examples. So here's example number 1. Solve each system of linear equations by substitution or elimination. So we get to choose what we want to do to solve these based on how they're set up. So when I look at example number 1, where it says 2x plus 5y equals 14 and 6x plus 7y equals 10, I see that everything is lined up, including the equal sign. And it'd be really easy to make opposites by changing this 2x into a negative 6 by multiplying by negative 3. So when I multiply by negative 3, I'd end up with negative 6x minus 15y equals negative 42. So that when I add downwards, the 6x, the negative 6x will cancel, and 7y plus negative 15y would be negative 8y, and 10 plus negative 42 is negative 32. When I divide both sides by negative 8, I get y equals 4. Now taking y equals 4 and plugging it back into either equation to solve for x, I'd get 2x plus 5 times 4 equals 14. So 2x plus 20 equals 14. Subtract 20 from both sides, and I'd get 2x equals negative 6. Divide both sides by 2, and I get x equals negative 3. So my final answer would be negative 3, 4. So here's a case where I did not get a weird answer. So sometimes you'll get an actual answer like we did here. Sometimes you'll get either no solution or infinite solutions. And let's see an example of just that in the next example. So here's example number 2. Again, we are told to solve each system of linear equations by substitution or elimination. So when I look at this problem, I first see that y equals 8x minus 1. So that makes me think that it'd be really easy to take the 8x minus 1 and plug it in for the y in the first equation. So I'd get negative 16x plus 2 times 8x minus 1, and that would equal negative 2. So the first thing I would do is distribute. So I'd get negative 16x plus 16x minus 2 equals negative 2. So these would cancel each other out, and I'd get negative 2 equals negative 2. Whenever your variables cancel out like they did here, or if you were doing elimination and both your x and your y eliminated each other, and you end up with a true statement like this, negative 2 equals negative 2. If you were doing elimination, it would be 0 equals 0. But in either case, this is a true statement. Whenever you get a true statement, your answer is infinite solutions. And we'll see later in the notes here what that actually means for a system of equations to have infinite solutions. And now let's look at example number 3. Again, we're going to solve by either substitution or elimination. When I see this problem, I see that it's already lined up, and it would be pretty difficult to get a variable by itself, so I'm going to do elimination. So I have a choice here. Either I could make the x's a 12x and a negative 12x, or I can make the y's a 10y and a negative 10y. Let's do the y's. So that means I would multiply the top equation by 5 since the 2 is already negative, so that would be my negative 10y, and I'd multiply the bottom equation by 2 to make it a positive 10y. So I would end up with 15x minus 10y equals negative 25, and then I would get 8x plus 10y equals 94. So when I add downwards, I end up with these canceling, and I get 15x plus 8x is 23x equals 69. So when I divide both sides by 23, I end up with x equals 3. So I automatically know that I don't have infinite solution or no solution since my variables did not cancel out and I did end up with an answer. Now taking that first answer, x equals 3, I would plug it back into either equation that I originated with. So I would have 4 times 3 plus 5y equals 47. 4 times 3 is 12. If I subtract 12 from both sides, I end up with 5y equals 35, and then if I divide both sides by 5, I get y equals 7. So my final answer would be 3, 7. So here is another case where my variables did not cancel out, so I do not have no solution or infinite solutions. I just have one precise place where the two lines would intersect if I were to graph them. Let's look at example number 4. Solve each system of linear equations by substitution or elimination. Here again, I see that everything's lined up, including the equal sign. So I'm going to go ahead and add downwards because I see that I already have opposites. I have x and negative x. However, these are going to cancel, but also the y's would cancel. Negative 2y plus positive 2y is 0. So I'd end up with 0 equals 14. So in this case, I ended up with both my x's and my y's eliminating each other, and I ended up with a false statement. Whenever you get a false statement like this, 0 equals 14, then your answer is no solution. If you did the substitution method, you would end up with something like 0 equals 10, and again, it would be no solution. So whenever you get a false statement, it's no solution. If you get a true statement, it would be infinite solutions. So what does this all mean? What does it mean for a system of equations to have no solution or a system of equations to have infinite solutions? The way you can tell is by comparing their graphs, and we can do that without solving. So this is how you can tell whether a system of equations has one solution, no solution, or infinite solutions without solving. So again, we're talking about graphing. So the first step when we're graphing is to always get y by itself. So the first step here is to solve each equation for y. Once y is by itself, what you're going to do is compare the slope and the y-intercept of each. If you end up with the same slope but different y-intercepts, that means the lines are parallel. Parallel lines do not intersect, so therefore there is no solution, meaning the two lines will never intersect. And remember, when we're solving a system of equations, we're looking for the place where the two lines intersect. So if the lines are parallel, they'll never intersect, so there's no solution. If you get y by itself, and you're comparing the slope and the y-intercept, if you get the same slope and the same y-intercept, that means the lines are the same. So if I graph a line and then graph the same line on top of it, those two lines are intersecting in every single place on the two lines. So therefore, there are infinite solutions. And again, that just means that the two lines are exactly the same, and where two lines that are the same lie on top of each other, then they're intersecting infinitely. They're always intersecting in every single point along that line. So again, if the y is by itself and you get same slope, different y-intercepts, that means they're parallel and we have no solution. If you get the same slope and the same y-intercept, that means the lines are the same and it's infinite solutions. So here's example number 5. Without solving the linear system, tell whether the linear system has one solution, no solution, or infinite solutions. So again, we do this by first getting the y by itself. So in the first equation, I would just need to move this 5x from the left to the right. By moving it from the left to the right, it would become negative. So our first equation would be y equals negative 5x minus 2. You could also put negative 2 minus 5x. It would be the same thing. For the second equation, I would first add 10x to both sides. So I'd end up with negative 2y equals 10x plus 4. If I divide both sides by negative 2, I'd end up with y equals negative 5x minus 2. So comparing these two equations, they have the same slope and the same y-intercept, so this would be the same line, which means they intersect infinitely, so they have infinite solutions. And now let's look at example number 6. It's the same instructions without solving the linear system. Tell whether the linear system has one solution, no solution, or infinite solutions. So again, let's get the y by itself. So let's take that first equation, 6x plus 2y equals 3. First thing I would do is subtract 6x from both sides. So I get 2y equals negative 6x plus 3. Divide both sides by 2. So I get y equals negative 3x plus 3 over 2. So there's our first equation. Let's take our second equation, 6x plus 2y equals negative 5. Again, the first step would be to subtract 6x from both sides. So I get 2y equals negative 6x minus 5. Divide both sides by 2, and I would get y equals negative 3x minus 5 over 2. So comparing these two equations, notice they have the same slope, but different y-intercepts. That means that these two lines are parallel, which means they would never intersect, so there would be no solution for this system of equations. And finally, our last example, number 7. Same instructions without solving the linear system. Tell whether the linear system has one solution, no solution, or infinite solutions. So again, we take each equation and get y by itself. So we have x minus 3y equals negative 15. I'm going to subtract x from both sides. So I have negative 3y equals negative x minus 15. Divide both sides by negative 3. So I have y equals, remember there's a 1 in front of there, so negative 1 divided by negative 3 is positive 1/3, and negative 15 divided by negative 3 is positive 5. So I'll take our second equation, 2x minus 3y equals negative 18. First thing I'll do is subtract 2x. So I have negative 3y equals negative 2x minus 18. Divide both sides by negative 3. So I got y equals negative 2 divided by negative 3 is positive 2/3, and negative 18 divided by negative 3 is positive 6. So comparing these two equations, they have different slopes and different y-intercepts, so that just means that these two equations will run into each other, and there would be one solution. So if you have different slopes and different y-intercepts, or even if you have the same y-intercept, you would have one solution. If you have the same y-intercept but different slopes, that means that they would just run into each other at their y-intercepts. I would write that down so that maybe it will save you some trouble down the road and maybe save you some work. That's it for this section. Make sure you jot down anything you don't understand that we can cover in class, and we'll see you then.